Let's talk about how to synthesize nanoparticles. There are so many nanoparticles, for example, gold nanoparticles, silver nanoparticles, metal oxide nanoparticles, such as titania, tin oxide, zinc oxide, iron oxides. So many materials are there. Synthesis basically means when you are making something. When you are making something, it is called synthesis. And synthesis is one of the major part in your research. When you go for your research, for example, if you are doing PhD or master, the first and foremost thing is literature. When you do the literature, so from the literature you know that what are the methods you are going to use. So you will use that method in order to synthesize something, so that the synthesis part comes. So the synthesis part you basically get from the literature, right? So now let's see what is nanoparticles. We know nano is a word which use for very small objects. Mean that when you make something like nanoparticles or nanorods or any kind of material whose one dimension is at least in the range of 100 nanometer. For example, we are working in 3 dimension, x, y, z, right? So at least one dimension of the object must be below 100 nanometer. So that stuff object you call nano. Now what is particle? Particle basically means that a small localized object. So for example, if we are talking about subatomic particle like protons, like electrons, like neutrons. So look, these objects have some physical and chemical properties. For example, physical property means that it contains some mass, some density, some volume, etc. Right? So this is, now you can see this is the nanoparticles, because this is I synthesize this using one kind of method. So there are numerous type of methods: green synthesis, hydrothermal, electrospinning, soluthermal, so many methods, but we will just focus here on one method. Right? So let's get started. In this work, I just synthesize tin oxide nanoparticles. So as I explained that nobody is going to synthesize or design a method from their own, but in research you just take help from the literature. We are improving the literature slowly and gradually, and we are creating more functionalities and more improvement in a kind of field. Like somebody made tin oxide nanoparticles before me, but what I'm doing now, I want to do some modifications in order to show that or to add some additional features to this material. So I am going to do the synthesis of tin oxide. So where I will know the method from the literature. This is the key thing, that I will know the method from the literature, right? So somebody says that sorry, I want to do my own method. No, you must need to do literature in order to get the method. Okay. So look this here, the material was synthesized following Wang et al. Wang et al. Paper is, I will show you later, and I just follow this paper. The method I took from this paper. So I'm not going to copy his method or her method. I will do some modification. But the method I took from this paper. So you must need to do literature. For example, if I go to Google and write here that, write this, for example, synthesis of tin oxide and nanoparticles, you see here. So you will see a lot of papers here. I picked up this. Look here, ACS journal. This is ACS. So there are so many methods. So if you know that this material has good qualities and good features, just download one paper, and this is good. This is the ACS journal, and this is also ACS journal or AC journal, Royal Society of Chemistry, and IOP. This is scientific. You see here. So many methods are there, and so many papers are there. For example, Springer, and go there and download paper and read the method and do some modification, right? So I just similarly I took one paper, I read one paper literature, and I got this idea. So the question is, how we will know that which material we have to choose? This is supervisor job, and again your literature you need to know the material properties. But with modification here, you see, in our experiments, we reduce concentration of the growth solution. We reduce this solution to nearly half. That we use this one, and the literature they use this one. You see here, this is the difference. We just reduce, because we reduce. Let's see how it works, right? The material was this dichloride. It is commercially available. This is the precursor. We took this much amount and we added to the one normal solution of HCl, this ethanol, and deionized water, right, in ultrasonic bath per hour, 1 hour. We put this in a solution and we ultrasonicate, we mix the stuff, right? So the resultant transparent solution was then transformed to autoclave, because I use hydrothermal method, as I explained. Very simple and very basic method. Just put in autoclave. Autoclave is a device just like to maintain pressure or temperature, and put the solution there and just tight the cap and put it in the oven, and then you will get the nanoparticles. So autoclave and keep the preheated furnace or to oven here. This is not our furnace, this is basically the oven here, right? Yeah, at 150 we already keep the temperature at 150 the oven. It just we put keep this autoclave. This autoclave contain this solution, right, for 24 hours. After cooling to room temperature, the solution was centrifuged. We centrifuge because we want to remove the water, because the particle now made, the nanoparticle made, and the solution is still there. So some particle grew, we will explain that how it grew the particles, and now we want to waste the rest of the solution. So we use the centrifuge. It's rotating and the particles are different masses now. The liquid particle have different masses and some nanoparticle have different. So now it's separate from each other, and we just remove and just we clean. Here you see, wash 3 times with dewater and dry it again. We dry the nanoparticle in oven overnight, right? That sample we just label sample A here, right? And we just want to know that what will happen if we increase the temperature of the oven. Here we keep the 150 at first, and we use the same parameters, but we just only change one parameter, that is the temperature of the oven. We just change the temperature of the oven to 150 and 180 to 200. And you can see here what changes we saw here in nanoparticle growth here. You see here, this is 150 here. So at 150, you can see we only see small particles here, nanoparticles. You see it is very small particles. It is almost 10 nanometer. You look this graph here, and this not 10 nanometer, about 20 nanometer. If you compare this bar here, so this is 30 nanometer we have, right? So if you look into the phenomena, now if we further increase the temperature of the oven, so you see there is a big particle growth start. So along with the small nanoparticles, there is a big particles, right? If you further increase the temperature to 200 degrees C, so you can see that those balls further grow and it made a very nice shapes. So you can see that this now contain some multifunctional features. For example, we have small nanoparticles and we have bigger particle in micron size, right? So this means that we have the combinations of both particles. I think if you further increase the temperature, I don't know, maybe we will get more this bigger balls or something. So this is how you do synthesis and synthesize nanoparticles using hydrothermal methods. So there are many other methods that how you will synthesize nanoparticles, but the most important thing is all information you need to get from the literature.